Hello my friends and welcome back to the Today Machine channel. The manufacturing of cylinder crankcases for large engines is a highly specialized process, driven by the need for precision, durability, and performance. Geninth, a global leader in this field, focuses on delivering state-of-the-art solutions for various industries. The process starts with casting, where molten iron or aluminum is poured into custom-designed molds. These molds are engineered to produce complex, optimized geometries that improve the power-to-weight ratio of the crankcase, ultimately enhancing engine efficiency. Once casting is complete, the crankcase is cooled and solidified. It then undergoes rough machining to remove excess material and prepare it for more refined operations. CNC machining is employed to achieve the tight tolerances required for large engine components. Following machining, the crankcase is subjected to heat treatments, such as annealing, to relieve internal stresses and improve its mechanical properties. The production process also includes drilling, honing, and threading to accommodate engine components and ensure a perfect fit. Throughout the manufacturing stages, rigorous quality control measures, such as ultrasonic and X-ray inspections, are implemented to detect and correct any internal defects. In the final steps, surface treatments like coatings are applied to enhance corrosion resistance and longevity. Cylinder crankcases produced by Geninth are also designed to support engines using alternative fuels, such as hydrogen, contributing to a more sustainable future. This combination of advanced manufacturing processes and stringent quality standards ensures the production of high-performance crankcases that meet the evolving needs of the modern world. The production of cast iron components has undergone significant advancements, driven by the increasing demands of modern industries. The process begins with the melting of iron in energy-optimized furnaces, where raw materials like scrap iron are combined with alloying elements such as carbon and silicon. This molten iron is then poured into sand or other refractory molds, which are specifically designed to shape the final product. Advanced molding techniques, including automated and 3D printed molds, are used to ensure precision and efficiency. Once the molten iron cools and solidifies, the casting is removed from the mold and excess material is trimmed away during the fettling process. To enhance the strength and ductility of the cast iron, heat treatments such as annealing or tempering are applied. Machining is a critical phase in the manufacturing process, where components are shaped to meet specific tolerances. CNC machining ensures that every part is produced to exact dimensions. Drilling, grinding, and polishing processes are often performed, depending on the complexity of the component. Quality control is a key element of cast iron manufacturing at Geninth. The use of material testing methods, such as hardness testing and ultrasonic inspection, guarantees that each component meets the required specifications. Additional surface treatments like priming or painting provide corrosion resistance, making the components suitable for use in harsh environments. These cast iron solutions are not only essential for today's mobility and energy sectors but also contribute to the development of sustainable, future-ready infrastructure. Geninth's long-standing expertise in metallurgy, combined with state-of-the-art manufacturing technologies, enables the production of highly reliable cast iron components. These components are critical for industries as diverse as transportation, agriculture, and energy, ensuring efficiency and sustainability in the global market. The manufacturing of a wind turbine hub, weighing approximately 35,000 kilograms, involves a highly specialized casting process. Utilizing mechanized molding systems and manual casting techniques, the process employs hand-molded cores produced using height-adjustable continuous mixers. The molds and cores are created with the fur resin molding process, ensuring dimensional accuracy and superior surface quality for large castings, which can weigh up to 65 tons. Muehlwitz-Guss offers comprehensive design support, replacing welded constructions with cast solutions, and advising on material selection and casting-friendly design. Their in-house model-making capabilities enable the production of precise models quickly, facilitating rapid adjustments and refurbishments. In the foundry, 3 medium-frequency induction furnaces with capacities of 12 tons each, and 1 furnace with a capacity of 36 tons, ensure reliable melting. The process is monitored by a 24-element spectrometer and supported by an automated charging system, ensuring high-quality molten material for each casting. The mechanical processing and coating of these cast components are handled by expert partners. This includes treatments like galvanizing, thermal spraying, priming, and painting, with documentation provided as requested. From the early design phase, technicians use advanced tools like solidification simulation, mold filling simulation, and deformation prediction during cooling. These technologies help improve the quality, reliability, and cost-effectiveness of the castings while reducing development time. Manufacturing injection and compression molds involves a complex and precise process designed to create durable, high-performance molds for various industries. The process begins with design and engineering, where mold makers collaborate with clients to develop molds that meet specific requirements for size, material, and performance. Advanced CAD/CAM software is often used to create detailed 3D models of the mold, ensuring accuracy before production begins. For injection molds, the focus is on creating molds capable of shaping thermoplastic materials under high pressure. These molds typically feature multiple cavities, allowing for high-volume production of identical parts. Precision machining, such as CNC milling and EDM, electrical discharge machining, is used to shape the mold components, which are then assembled and polished for smooth operation. In contrast, compression molds are used for molding thermoset materials and carbon fibers. These molds are designed to withstand high pressure and temperature, ensuring the proper curing of materials. The manufacturing process includes similar precision machining but with specific considerations for thermal management and material flow. In hand-molded casting for a crankcase, the mold assembly process is essential to ensure a precise and durable casting. At Muehlwitz-Guss, the mold pieces are carefully prepared and assembled in the casting pit. The process starts by positioning the pre-manufactured mold sections, including both the cope, upper part, and the drag, lower part, in a pre-dug pit. The mold is typically composed of sand reinforced by binders to provide the necessary rigidity and detailed contours. For crankcases, the mold is designed with multiple sections to capture complex geometries, including internal passages and mounting points. Once the individual mold sections are in place, they are precisely aligned using alignment pins or guide systems. This ensures a tight fit between the mold halves, reducing the chances of casting defects such as flash or mismatch. Core placement is another crucial aspect of mold assembly. Cores, often made from hardened sand, form the internal cavities of the crankcase, such as the areas for oil channels and bearing surfaces. These are positioned inside the mold according to the design specifications. After the mold assembly is complete, heavy plates are inserted on top of the mold structure. This plate helps compress the mold, ensuring that it retains its shape during the high-pressure casting process and preventing any shift or distortion when the molten iron is poured. The molten iron, prepared in a furnace, is heated to the appropriate casting temperature, which typically ranges between 1200 degrees Celsius and 1400 degrees Celsius, depending on the material specifications. Once the iron is ready, it is carefully poured into the mold through designated gating systems. These gates and risers are designed to channel the molten metal smoothly, filling the entire cavity while avoiding turbulence, which could introduce defects. After filling, the mold is left to cool, allowing the molten iron to solidify into the desired crankcase shape. The process of pouring molten metal into cast iron molds is a critical step in metal casting, typically used to create complex metal components. In this process, molten metal is poured into a mold cavity formed in cast iron, allowing it to cool and solidify into the desired shape. This method is particularly popular due to cast iron's excellent heat retention and resistance to deformation during the cooling process. Before pouring molten metal, the cast iron mold is carefully prepared. The cavity inside the mold is designed to match the dimensions of the final product, with allowances for shrinkage as the metal cools. For example, the shrinkage rate for metals like steel is around 2%, while aluminum shrinks about 1.3%. The mold also includes risers and runners to allow for proper flow of metal and gas escape. In many foundries, the molten metal is produced using an induction furnace or a cupola furnace. For instance, a 3-ton induction furnace can melt steel at temperatures ranging from 1400 degrees Celsius to 1600 degrees Celsius, depending on the alloy. The melting process can take 1 to 2 hours, depending on the batch size and type of metal. Once the metal reaches the desired temperature, it is carefully transported to the cast iron molds, typically using a ladle. The ladle must have sufficient capacity, such as a 500 kilograms or 1000 kilograms capacity, depending on the casting size. The pouring temperature is crucial. For cast iron, it ranges between 1150 degrees Celsius and 1250 degrees Celsius. A controlled pouring rate ensures the mold is filled evenly, minimizing turbulence that could lead to defects like air pockets or inclusions. This can take anywhere from 30 seconds to a few minutes for larger castings. After the mold is filled, the metal begins to solidify. Cooling rates vary depending on the type of metal and mold thickness, but generally, it can take between 30 minutes to several hours for the metal to fully solidify. A thicker mold may require more time to cool, while thinner molds cool faster. For large castings, cooling times can extend up to 24 hours to avoid internal stresses or cracking. Once the metal has solidified and cooled sufficiently, the mold is broken apart to release the casting. Any excess metal from risers or runners is removed, and the casting undergoes finishing processes such as grinding or heat treatment to achieve the final specifications. This moving column milling machine operates by shifting the milling head along a fixed bed while the workpiece remains stationary. This design allows the machine to handle large parts with varying shapes and dimensions, making it highly versatile. The machine's main movement is guided on a robust bed reinforced with internal ribs, ensuring system rigidity. The milling process takes place with the column assembly, which moves in three axes, X, Y, and Z. The X-axis carriage moves the column along the bed, guided by two linear tracks, supported by sliders with roller recirculation. The double rack and pinion system powers the X-axis, providing stability and precision when machining long parts. One of the key advantages of the moving column design is its ability to machine parts independent of their location and fixings. This flexibility enables the machine to accommodate a wide range of part sizes and shapes, whether large or heavy. The high accuracy and repeatability of movements, combined with guide tracks, ensure precise machining. For operator comfort and control, the machine is designed with an accessible cab, either fixed or with vertical movement, and dual control panels for easy operation from both the cab and the machine's front. This setup allows for efficient monitoring and adjustments during the machining process. The Lagan bed mill is a robust, modular milling machine with an integrated rotary table, designed for flexibility and precision. Its rotary table offers high load capacity, enabling the machining of long or complex workpieces. With interchangeable components like slides, rams, and columns, the machine enhances rigidity and ergonomic comfort for operators. It has a longitudinal X travel of 3, 4, or 5 meters, making it ideal for large-scale or five-sided milling. The machine's optimized working area and internal space allow for machining various shapes and sizes, while efficient swarf and coolant removal ensures smooth operation.